as part of the GeoPRISMS Distinguished Lecturer Series. Professor Holbrook got his bachelor's degree in 1982 from Penn State, master's and PhD from Stanford in 1989. Then went to Woods Hole Oceanographic Institute from 89 to 97, and then ended up at University of Wyoming up until the present day. He is a marine geophysicist who is also a fellow of the AGU. He's been elected a fellow of AGU this year. And he's been on at least 15 cruises so far, so spent about 1.5 years out in the sea. Okay, and today he'll be giving us a talk on the subduction zone, subduction sponge, mantle subductionization of the downgoing plate.
Thank you, Ali. Can I control the lights from here?
Yes.
It should go off. Okay, it might even be best to turn all of them off, yeah, just to get there. I think it'll show up better. So thank you very much for the invitation to come to Marshall. I'm very happy to be here. It's a beautiful place. I've never been here before. Although I understand that there's a possibility that Marshall and the University of Wyoming may be joining the same athletic conference. So, because I think that you guys are Conference USA, right? And we're Mountain West, and we're going to merge to make some kind of super conference because all the big boys keep leaving our conferences. Anyway, so it's a real pleasure to be here. I am going to be giving 2 talks today. This first one is the more specialized talk, and then later this afternoon I'll give another talk on arcs and the andesite paradox. But I want to encourage you all, because I know there's probably no marine geophysicists in the room or people that are even that familiar with marine geophysics. So I want to encourage you to please interrupt me if you have any questions. If I say something and it's just going right over your head because you haven't had a class in this or anything. I tell my classes this at Wyoming too, just interrupt me. Put your hand up or just speak out, and I'll be happy to explain anything that's not clear. So here's an overview of what I'm going to talk about today, what I call the subduction sponge. And basically the bottom line here is, in a subduction zone where you have a downgoing oceanic plate, oceanic lithosphere going down, it's oceanic, it's under the ocean, and those plates, it turns out, suck up a lot of seawater by a couple of processes that then goes down into the subduction zone and has a broad array of consequences for plate boundary strength, for fluid cycling. If you want to understand the water cycle on planet Earth, you have to understand this subduction sponge. The chemistry of the eruptive products of volcanoes, seismicity or earthquakes that are happening inside the slab, and even perhaps the deep biosphere. So the way I'm going to organize this talk is I'm going to start with just what's the mechanism, how is this, what's creating this subduction sponge, why are these plates sucking up seawater and taking it down the tubes, and I'll show you the evidence for this, which is largely a set of geophysical observations. Okay. All right. And then we'll talk a little bit about the consequences and why we should care. So to start the topic, I like to go back to a paper that Doug Masson published more than 20 years ago now, where he compiled what was known at the time mostly from seafloor bathymetric and seismic reflection profiles about the structure of oceanic crust, oceanic lithosphere, on its way into a trench. So these are all subduction zone profiles. This is the outboard part of the subduction zone. So in this orientation, all of the I'm just going to use my hands, Ali, if that's okay. All of the plates are subducting to the left underneath. The landward part, the upper plate, the trench is right here. The arc volcanoes would be off the slide to the left. And when I see this picture, and what Masson was saying was, well, look what happens when the plate approaches the trench. It's bending, and when it bends, it cracks. And we can see the cracks in the form of faults, and the seafloor becomes highly faulted right outboard of the trenches. And this, I'm reminded of Samuel Coleridge Taylor's Rime of the Ancient Mariner. This is the couplet that immediately precedes the more famous couplet. water everywhere, and all the boards did shrink. He's talking about the seawater and its effects on the boards on the ship, and this kind of reminds me of that kind of effect. It's not exactly a perfect analogy, but anytime I can throw a little bit of poetry into a science talk, that's a good thing. So, and this is also from Masson's paper, and he compiled on a global map trenches where he saw that this seemed to be happening, and he drew little parallel sets of lines. Tonga Trench, the Aleutians, Japan, Java, Middle America Trench. I'm going to be talking a lot more about this part of the world here in my talk, the Middle America Trench, the Peru Trench. And he said, look, this is happening at a bunch of places around the world. Don't have a lot of data as to where it's happening, and the orientation of the lines was meant to show what was known at the time about the orientation of the faults. So, why does this happen? It's happening because the plate is bending, and you're getting stresses inside the plate from that bending. And Quesada et al. Published a paper a couple years ago where they did a very nice, very thorough numerical modeling study of this process. And what they were looking at in particular is, what's the distribution of tectonic stress inside a plate like this when you bend it on its way into a subduction zone? And a surprising thing comes out of this, that when you bend a plate like this, you can actually derive very subtle changes in tectonic pressure that will actually drive negative hydrostatic gradients. So water will actually get pulled down into the slab. And that's what this is a cartoon, which is, well, it's not really a cartoon, it's a visualization of the result of one of their numerical models, where they show that the expected response of this plate as it bends on its way into a subduction zone is to draw pore water, to draw seawater down into the plate. And when you draw water into the mantle of a subducting oceanic plate, the mantle has ultramafic minerals in it, olivines, pyroxenes, and those minerals will serpentinize, right? So you're going to drive reactions that take ultramafic minerals and create serpentine. So things like antigerite and chrysotile and lizardite, these serpentine minerals that are water-bearing hydrous phases. So you're locking up water, seawater, into the mineral structure of the downgoing plate, and then you're sending that water down into the subduction tubes. And Quesada, so they did a very detailed numerical model. They even looked at the strain that you would expect in the plate, and you can see here they're predicting sets of conjugate extensional faults. And these faults provide pathways for water to get pulled down into the downgoing plate and produce serpentinization. So this raises a lot of questions. How widespread a process is this? How much water is being pulled into the plates and subducted? What happens to the water once it's there? Does it all go down? How much of it gets out? All kinds of things like this. So there's good evidence that this is actually happening. This isn't just something that someone's dreaming up and sitting on and making a computer model and imagining that this might happen. In fact, the computer model was in response to some really clear geophysical evidence that this process is happening, that it's widespread, and that it's important. So I'm going to show you three different kinds of geophysical evidence for this process. Reflection images, seismic velocities from refraction data, and electrical resistivity data. And there, just to finish off, there's the more well-known couplet from Taylor's Rhyme of the Ancient Mariner. So first, I'm going to tell you a little bit about how marine geophysicists or marine geologists map the seafloor. In case you're not aware of this, nowadays all modern research vessels are equipped with multi-beam sonar systems. So these are sonar systems. You send out a ping of sound, and you wait for the reflection to bounce back. You measure the time it takes for that reflection to come back. Because we know how fast sound travels in water, then we can turn that into a depth. And these days, the multi-beam part of this is you're not just sending a beam straight down below the ship, but you're actually sending out a swath of beams over these sets of angles, and then each one of those is bouncing in a different spot. And so you're actually mapping a swath of bathymetry as the ship goes along. And the width of the swath is a function of the angle, which depends on which instrument you bought. You want to get wider angles, you pay for the more expensive system. And the water depth, right? If you're in shallow water, then when you cross this set of beams, it's not very wide, and when you're in deep water, it's much wider. So then the ship goes along and mows the lawn. It's literally, that's what we call it when we're out at sea, mowing the lawn. It's just like you mow your lawn and you missed a spot, so you got to go back, drive back over it with the lawnmower. In this case, you have to drive back over it with the ship. It's a little more time-consuming and expensive. So in the Middle America Trench, this is a resulting data set of a number of campaigns of multi-beam sonar mapping of the downgoing Cocos Plate. So where are we? Here's the coastline right here. This is the Middle America Trench. Here's the trench axis right here, the deep blues. So this is the deepest part. This is Costa Rica. This is Nicaragua. You can just see Lake Nicaragua right there. So what's happening here geologically is the Cocos Plate is subducting in a northeast direction underneath the Caribbean Plate, and there are arc volcanoes back here in Nicaragua and Costa Rica. There's one of them right there as a result of that subduction. So this is all the offshore portion. You can see some of the ship tracks. You can see where they missed some spots. Here you can see what the swath width is from one of those, one ship track going around. But if you mow the lawn, and this is the result of a number of campaigns conducted by mostly German researchers in Kiel at Geomar, and they produced a remarkably detailed image of the seafloor. And what you see here is in the downgoing Cocos Plate, you can see this fabric right here. And these are the surface expression, the seafloor expression of all those faults that are chopping up that downgoing plate as the plate bends. And you can see as you move farther away from the trench, the faulting isn't there yet, or it's much more subtle. And there also appears to be a change as you go from off of Nicaragua to off of Costa Rica in the width of the faulting zone and the strength of the faulting. So this got a lot of people's attention. And this is work by Cesar Renero, and then in the same paper, Cesar published a reflection image, which I'm going to show you in a minute, that also turned a lot of heads. First, I want to introduce this method of reflection seismology. This is my specialty. So you go out with a specially equipped seismic vessel. That vessel is towing a long cable that's got hydrophones in it. It's a cable about this big around. And hydrophones are like underwater microphones. They're sensing pressure variations in the water. That cable can be 6, 8, 10 kilometers long. So very, very long cable with many hundreds of channels of hydrophones in it. And then in front of that cable, you're firing some kind of a pneumatic sound source, airgun bubbles that make a clapping sound, and the sound waves from that then go out, and these are rays drawn. So the sound waves, of course, are sort of spherical, but this is showing the direction of propagation of that sound. It goes down, it bounces off the seafloor, bounces off of any geological discontinuities that are beneath the seafloor, and then all of these returns are recorded, sent back to a computer on the ship, and then from processing of these, we can make very detailed, what look like cross-sections inside the Earth. You've probably seen some of these if you've this is the main technique that oil companies use. This is just an example. This is actually from one of my cruises off of Norway. Just to show you, I want to start with an example in sediments before we look at Cesar Renero's image of the faults in the Cocos Plate. So here you can see, here's the seafloor. This is actually, we went here to study this submarine landslide. It's called the Strega landslide. It's one of the largest submarine landslides on Earth. And you can see the scar of the landslide and all this disruption in here. You can get very detailed pictures. And in fact, if you zoom in on this box, see this little pattern right here, this little sort of zigzaggy pattern. If you zoom in on that and plot it at 1:1, so no vertical exaggeration, just like geologists, we geophysicists love our vertical exaggeration. This is a very rare picture. This is a seismic reflection image at 1:1, no vertical exaggeration. And when you do that, here's that zigzag pattern. Anybody have an idea what these are? Sorry? They're not folds. It's a good guess. This is bookshelf faulting. Right? Here are the faults. So these strata were horizontal, connected. There are the strata, dipping back like that. Here are the faults. And so it's a set of faults that just back tilted all of these strata like that back along these faults. Anyway, the point is you can get very, very detailed images of structures and stratigraphy inside the Earth using this method. So here's Cesar Renero's image. Now we're going back to the Middle America Trench. Here's the trench axis. So Nicaragua would be up the continental slope this way. This is all Cocos Plate, direction of subduction down to the right. And what you see here is, just focus your attention on the seafloor right up here, and you can see all these discontinuities in the seafloor. That's the expression of all those faults we saw in that multi-beam image, right, that run along sort of parallel to the trench. And then if you squint, or if you're a trained reflection seismologist like I am, you will see right here some sort of horizontal low-frequency reflections. There are helpful white dots here to guide the eyes of the untrained. If you're ever in an interview, by the way, with an oil and gas company, and sometimes the companies will bring to the interview seismic section, it won't be as hard as this, it'll be more like the last ones, and ask you to interpret it. You can always impress them if you kind of, what people do is they'll roll it out, and if you get your face down on the table and look at it edge on, so that you're getting some false vertical exaggeration, that shows you've looked at this stuff before. So I can see from where I'm standing the moho right here. These dots are the base of the oceanic crust. So there's the oceanic crust. There's sediments on top, all these layered things. Top of layer 2 in the oceanic crust. Here's the moho. And what was remarkable about this image is all of this stuff. You see this fabric of reflections, these images that are oriented down towards the trench. And what Cesar proposed in this paper, which was published in Nature almost 10 years ago now, is that these are reflections coming off of those faults, just like in that image I showed you a couple slides ago with that bookshelf faulting. You could see those reflections coming off of the fault plane surfaces. He said these are fault plane surfaces. They track up to, some of them you can actually track right up to where these discontinuities are, and they're going well down into the mantle. This is the moho. This is the upper mantle. In the upper mantle, this scale bar right from there to there, 2 seconds would represent 8 kilometers, because the speed of sound in ultramafic rocks is 8 kilometers per second, so 2 seconds down and back is 8 kilometers of travel path. So there's your 8 kilometer scale bar, because this is in two-way travel time. So these are going down 15, 20 kilometers into the upper mantle. This turned a lot of heads and has really kicked off a whole new direction of research in trying to understand serpentinization, because if these are faults that are allowing water to get down into the upper mantle, there could be a significant amount of water stored in the upper mantle on its way into the subduction system. So how would we know if seawater is getting down here and actually causing serpentinization? Because this image doesn't do it. This image says, well, there are possible pathways. There are faults that we're imaging. So maybe seawater is getting down there. There's a mechanism. Well, sorry?
Wouldn't you need terms of water to get a gas? Because the downward motion means that the water comes into the sea?
Well, there's high pressure as well, so you could actually have liquid water at much higher temperatures than just 100 degrees C. And once it gets down there, it probably is going to react with the minerals around it and get chemically bound through these serpentinization reactions, right? Unless it's too hot. If it's above 600 degrees or so, then no more serpentinization. So, how would we know whether this serpentinization process that I just described is happening? Well, one way we would know is by looking at the speed of sound, or the P velocity, the compressional velocity. P stands for primary, so 2 kinds of body waves in seismology, P waves and S waves, primary, secondary waves. P waves are the faster traveling, first to arrive, therefore primary. And what's shown over here is from Javier Escartin's paper in geology in 2001. Most of the lab data here come from Nick Christensen and some others. And what's plotted here is P velocity versus density as a function of serpentinization. So these are all measured P and S. This is actually S velocity down here, so primary, secondary velocity. For pristine ultramafic rocks, peridotite, that would be up here, 0% serpentinization. And then more and more completely serpentinized rocks. So this would be, so 100% serpentine would be over here. And what happens is there's a pretty nice linear relationship between the degree of serpentinization and the P velocity. Because serpentine minerals have they're slower rocks from the geophysicist's point of view. Speed of sound is slower. Fast in in pristine peridotite, slow in serpentine. So this gives us a tool to try to explore for whether this serpentinization is happening by trying to map out P velocity. And we can do that with seismology as well. And the lower the seismic velocity, the higher the degree of serpentinization. That's important. So again, the Germans have led the way here and did a number of surveys where they used ocean bottom seismometers. So you put a seismometer on the seafloor. That records the same air gun shots that are being fired from the seismic vessel, but at much longer offsets. So you can measure the amount of time it takes the wave to go over different distances, and the slope of that curve gives you velocities. It's pretty simple. It's a little more complicated than that in practice. You do tomographic conversions and that sort of thing. But basically, it's like going out with some seismometers on the ground, swinging a sledgehammer, and you measure the time it takes to go over a certain distance, and you divide and you get a velocity. That's about what it is. So the Germans went out and they did some surveys, 5-10 years ago, to try to test whether there was evidence for serpentinization down here. And what they found, as you probably could guess, or I wouldn't be standing here today, is yes. So here are some maps of P wave velocity inside the crust and upper mantle. So here's the moho. Now we're looking at depth, and we're looking at 100 kilometers or so horizontally. So this is section P01, P02. If I go back here, that's these two profiles. So along the Cocos Plate in the area where these faults are seen. And so this is a paper published by Monika Ivandic and others just a couple of years ago. And I'll help you out here because you might not be able to read these labels. This is the moho, the normal P velocity of the upper mantle. Anybody know what it is? Ish? About 8 kilometers per second. I always tell my undergrads, if you want to understand crustal seismology, you just need to know 6, 7, and 8. 6 kilometers per second is granite. 7 kilometers per second is gabbro. 8 kilometers per second is upper mantle. So that's upper crust, lower crust, and mantle. 6, 7, and 8 kilometers per second. So normal upper mantle is around 8 kilometers per second. These numbers say 7.4, 7.6. Here's 7.4, so just below the moho, they're actually a little lower than 7.4 kilometers per second. 7.3 to 7.4 kilometers per second. Oh, I just asked you a question. I do this all the time in my lectures too. I put the answer up here, and then I pose this question to my students, and then I'm always impressed when some genius tells me the answer, and then I realize, oh, geez, there it is. This is the normal upper mantle velocity. This is what's observed. What does that mean if we go back? I won't do it, but if we go back to that figure of the lab velocities and that linear relationship between P velocity and degree of serpentinization, this implies something like 25% serpentinization of the upper mantle here. That's a pretty fair degree of serpentinization, a pretty fair amount of water. So this raises some questions. Does this vary systematically along the trench? Does it vary systematically with the degree of faulting that we can see and with the angle that the faults make with the trench axis? Why do we care about this? Well, one reason is, and this always amazes me, this process that's happening well offshore in the downgoing Cocos Plate is actually more than likely having an impact on some of the trace elements that are being erupted out of the volcanoes, which are 150 kilometers farther onshore. And so here's some geochemistry. I'm not a geochemist, but I'll give you a geophysicist understanding of what these plots mean. So we're looking at distance along the trench, or along the arc. These are all measurements of geochemistry from arc volcanic rocks. And we're going north to south from Guatemala, El Salvador, Nicaragua, Costa Rica. So down here is where we've been working, and the data that I just showed you are from about here, right about here. This is barium lanthanum. This is the terbium lanthanum ratios, and then this is the slab dip angle. So I don't want to focus too much on this right now. But these ratios, for example, the barium lanthanum ratio is thought to represent, so this is a ratio of a fluid mobile element to a fluid immobile element. So when this ratio goes up, you've got a lot of fluid mobile elements in the arc rocks. And what that means is there's probably a component from the slab, because that's where the fluids could come from. All these fluids that are being trapped in the slab, not just in the serpentine, but even more so up in the upper oceanic crust where you've got porous rocks and hydrated minerals in the oceanic crust and sediments that are loaded with seawater. That stuff's coming out in Nicaragua. This is a global peak. These numbers of 100, 125 in this ratio, there's no place on Earth that's got a higher ratio. And then it dives down to Costa Rica. So there's this really interesting gradient in this indicator of what people call the slab component of arc lavas. So there's also a decrease in seismic velocity off of Nicaragua. I just showed you that in the Avondich figures. So that makes it pretty tempting to conclude that maybe it's the hydration of that downgoing plate and all the water that's being trapped in serpentine minerals in that plate that's actually controlling this signal. And that would say that there's less. There should be, and that gives us a prediction. That's always something good in science. We want a prediction that we can go out and test with an experiment. And that says there should be less of this off of Costa Rica. So we, my colleagues and I, did a very large-scale seismic survey almost about 4 years, actually 4 years ago right now, going across Costa Rica. We did, so these lines, these yellow lines offshore are our ship tracks. We did a cruise with the Marcus Langseth. I'll show you a picture of the Langseth in a minute. In the Caribbean, then went through the Panama Canal, and then did another month-long cruise in the Pacific. And one of the highlights of this, and something I'll talk about in my second talk today, is this transect going across the arc. We wanted to understand the structure and composition of this arc here, because I'm interested in what creates continental crust. But what I'm going to talk to you now about is a couple of lines that are offshore over here. So one of the lines that we designed was this long line that went all the way along the trench from Nicaragua to Costa Rica, continuous line. And this was designed specifically to test that prediction, that we should see higher upper mantle velocities, therefore less serpentinization down here than up here. We want to know, is there a correlation between the offshore upper mantle P-wave velocity and the geochemistry of the arc lavas? It's kind of a wild idea that those two things should correlate, but that's what we wanted to test. So this is my favorite ship. It's the Marcus Langseth. This is owned by the National Science Foundation. This is the academic seismic research vessel. Anybody can use it if you get a proposal funded to go out and do marine seismology. It's specifically designed to do marine seismics. It's a wonderful platform, can even do 3D seismics. It's operated by Lamont Doherty Earth Observatory, which is part of Columbia University. This is obviously not Costa Rica. This is very close to where my favorite baseball team plays, which is just around the corner there. And this is a former industry seismic vessel. It used to be called the Western Legend, was owned by Western Geco, was purchased by the National Science Foundation on behalf of Columbia University, and now runs around the world's oceans. One of my postdocs is out there on the ship right now, having just sailed from Guam to go do a survey. So this runs around the world all the time and just collects seismic data for science. Wonderful thing. We also, on this survey, deployed a bunch of these ocean bottom seismometers that I told you about. This is a picture of what an ocean bottom seismometer looks like. It's being deployed. I can tell it's being deployed from the lines and the fact that the anchor is still on it. So these sink down. They're autonomous instruments. They sink down. They rest on the seafloor on this anchor plate. And then when we're done recording, we go back. We talk to it. It releases with an acoustic release from its anchor plate. And then these are glass spheres underneath these protective hard hats that provide buoyancy. So absent the anchor, this whole instrument is buoyant and rises up to the surface, and then you go collect it with the ship, bring it on board, download the data, and have all kinds of scientific fun. So these were deployed from we had two ships on the Pacific side, the New Horizon, which is a ship run by Scripps. We did about 80 deployments, and these recorded wide-angle seismic arrivals. So back to our cartoon, what the ocean bottom seismometer does is it sits here on the seafloor. So that thing would sink from the ship on its anchor plates, rest right there, and then it would record rays that have a different path and could go out to very long offsets indeed, as you'll see in a minute, and record all these sound sources from the vessel. So here are the lines. I'm going to talk about two lines here. This is the first one, the Serp Line, and you can see that it starts up here in this area where all these seafloor faults, they're very prevalent, very clear, and continues down to here where they're basically absent. So our prediction for the velocity structure here would be low upper mantle seismic velocities, i.e. lots of serpentinization, and less as we go down to the southeast. The data looks like this. This is the data that we get back from the ocean bottom seismometer. I'm not going to dwell on this. But hopefully you can all see these arrivals, these coherent phases that are coming across like this. So the analysis method is to go in there and pick the travel times on here and then build a computer model that matches those travel times and tells us about the distribution of seismic velocity inside the Earth, which looks like this. So we're going from northwest to southeast on that line that I just showed you. The white is ocean. Here's the seafloor. These little dots are the locations of all the ocean bottom seismometers we put out. This solid line right here is the MOHO. So right here is the oceanic crust. Pretty uniform thickness in what's called the EPR segment. This is crust that was born at the East Pacific Rise, Mid-Ocean Spreading Center. Farther south, this crust is a little more complicated, was born at a different mid-ocean ridge, the Cocos-Nazca Spreading Center. And so what I want to focus your attention on are these upper mantle velocities right here. I think you can see, just with the color scale, that there is indeed a change as you go from northwest to southeast. These are quite low velocities, around 7 kilometers per second, or even a little bit lower. And these numbers would imply average degrees of serpentinization in this upper mantle of about 30%. 30% serpentine minerals, replacing the peridotite down there. Just a plot showing the ray coverage and travel time fits so that you can, this is just to convince you that we have good ray coverage from our data so that our tomographic inversion, this is like doing a CAT scan inside the Earth. It's well constrained. All right, so here's a map looking down, and I've rotated north now so that, or I should say Harm van Avendonk, who was the first author on this study, rotated north. So now the trench is oriented horizontally here. So here's the trench, here's our line, and then what's plotted above the line is seismic P velocity in the upper mantle and in the lower oceanic crust. Okay, these lines with error bounds on them. And what you see is this trend in the upper mantle going from lower to higher as we go down to the southeast, which pretty much matches the distribution of faulting. Lots of faulting, much less faulting. So far, so good. We probably should have stopped there, because it's a nice clean story. But no, we couldn't leave well enough alone, and I noticed, looking at these seafloor bathymetric images, that in fact there's some faulting off of Costa Rica down here, and I'll zoom in on this in a minute so you can see it better. So we laid out another line, which we called CR Serp, for Costa Rica serpentinization, question mark. And I'm going to show you the results of that. Here's a zoom, and so now I hope you can see. So here's off of Nicaragua, northern Costa Rica, Nicaragua. Here's all that seafloor faulting. Kind of wanes and peters out down here. Our Serp line came down about like that, actually crossed like this. And then right here you can see the seafloor off of Costa Rica is also faulted. The faults have a different orientation. They're oriented slightly obliquely to the trench, but they're there. And so I wondered when I was planning the survey, well, I wonder if there's serpentinization under there, because on the basis of the faulting, I would expect yes. On the basis of the arc geochemistry, I would think no. So that seems kind of interesting. So I'm going to show you a reflection image right along this line. To orient yourself, this is a seamount, Fisher seamount. So that'll show up very clearly in the reflection image. There's the seamount. Lots of vertical exaggeration on this plot now. And all I want you to focus on is the seafloor to the west of the seamount, the northwest and the southeast. Lots of seafloor faulting. Here you can see the faults in the seafloor, and not so much over here. So Eric Everson, one of my graduate students, has been working on this, and we have a paper that's just about to be submitted to G-Cubed on this. And here are Eric's results. So we have good data, pick the data, model the data, good ray coverage on both sides of this seamount, and here is the resulting model. 8.1 kilometers per second on this side of the seamount, 7.5 kilometers per second on this side of the seamount. So where the seafloor faulting exists, indeed, there's strong evidence of upper mantle serpentinization. So that's kind of an expected result. It's about 15% for 7.5 kilometers per second. So it's not as spectacular as up off of Nicaragua, which maybe holds out some way to reconcile these two apparently disparate results. So this tells us that upper mantle serpentinization occurs even when the faults are oblique to the trench. This surprised us a little bit until we read Magali Billen's geology paper, where she actually looked, she did a sort of more Coulomb stress analysis of the situation for where you had faults, where you had abyssal hill fabric, that was oriented very closely to the trench. And it turns out that what happens there is you reactivate this abyssal hill fabric and the faults that came from the mid-ocean ridge. So the orientation of the ridge at which this oceanic crust was formed determines the orientation of these dashed lines. And if that's close to the trench, then the energetically most efficient thing to do is to reactivate a fault there. But if the angle of that fabric is more than 25 degrees, this comes from Billen's analysis, more than 25 degrees from the trench, then you can't reactivate those and you break new faults, which is probably much harder to do. And it turns out that the angle of these faults, so here you can see that angle, what she's calling alpha sub h, is about 20 degrees. These faults are about 20 degrees from the trench axis. That's less than 25, so they're probably being reactivated, and those are the pathways of the serpentinization. Okay, very quickly I'm going to talk a little bit about some other geophysical data, in particular magnetotelluric data. Magnetotelluric, fancy word, all it means is it's using variations in the Earth's field. The Earth's magnetic field is always varying. When it varies, it creates electrical currents, right? Varying magnetic field generates electricity. Those electrical currents can be picked up by meters that are designed to do that. And then you can actually build, if you have a bunch of these instruments out, recording the electric field, and you know what the magnetic field is doing, you can actually build an image of resistivity. How resistive is the inside of the Earth to the flow of electrical current? That's resistivity here in ohm meters. Okay, and so Vorshevsky et al., in a paper just published last year in Nature Geoscience, did a magnetotelluric survey, basically right off of Costa Rica. Here's the Nicoya Peninsula, very close to where our lines are. It's very interesting results. So the color scale here is blue is resistive. Okay, so it doesn't transmit electrical currents very well. So that's here and here. And then as you go more towards the red, that's low resistivity, which means high conductivity. So very conductive to electrical currents, like here, here. So there are these anomalies that they found. The thing I want to focus your attention on is this change in the upper mantle. So here's the upper mantle of the Cocos Plate, and it's blue. It's resistive, which is what you'd expect. But as you approach the trench, that changes, and the resistivity goes down by a couple of orders of magnitude. Vorshevsky made a nice 3D cartoon showing what they think this means. So these colors are the same colors from that image that we just saw, and they've made it 3D and some interpretive stuff. And they're saying that that's right where this faulting happens. We're getting seawater penetrating into these faults, going down and decreasing the electrical resistivity, which is what you'd expect for those minerals, on the way in. So this is a completely independent set of geophysical evidence that major changes in physical properties in the upper mantle of the subducting plate are happening, coincident with this faulting. There are other places in the world where this is seen. Here's another example offshore of Chile, again from the German group, Contreras-Reyes et al., published in JGR a few years ago. Here's the upper mantle velocity. It's 8.3, 8.4. It's actually a little faster than normal. This could be due to some anisotropy. And then as you approach the trench, where there are some faults, 7.8 on the way down. There's a nice reflection image off of Chile as well by that Ingo Gravemeyer published in EPSL a few years ago. It's very hard not to interpret this reflection as a fault. It projects right up to observe fault in the seafloor. And here I think even the untrained eye can see the moho. This fault, it looks kind of listric at the base, and it's penetrating well down into the upper mantle. So we still don't have, going back to Doug Masson's figure, we still don't have great global coverage. I mean, I think this is a great opportunity for future work to try to understand better where this process is happening and do some hypothesis tests along the lines of things that we've been doing off the Middle America Trench and others have been doing elsewhere. We still don't have a much better understanding than we did 20 years ago about this because it takes a lot of time and money to go out there and get these kinds of bathymetric maps and geophysical data. I think it's really well worth doing. Why? Why do we care? Well, if you, like I said at the beginning of the talk, if you want to understand the fluid budget on this planet, there is a lot of water that's actually being trapped in this downgoing plate, and that water has, this is a figure from a paper by Lars Rupke and others, a very nice paper trying to look at the fluid budgets and actually try to put some numbers on some of these parts of the budget, where we have water that's being sucked into the subduction sponge here underneath the plate bending faulting. But that water is escaping, and we know it's escaping. We don't know the full budget, but we know that we're getting discharge up here in the forearc. There are a lot of seafloor seeps that have very interesting life forms. They're like these vent communities around black smokers on mid-ocean ridges, but they're cold seeps, methane seeps from fluids that are coming out in the forearc. We don't have a good handle on how widespread those are, but we know that they're there, and they're very interesting for a lot of reasons. We know that the upper mantle in the mantle wedge can be serpentinized, probably by fluids that are being released by a series of metamorphic reactions that are occurring as the plate goes down and successively warms and then starts to dehydrate. Different minerals at different depths. And ultimately, these fluids are probably the fluids that are sourcing flux melting in the mantle wedge, which is why we have volcanoes in arcs above subduction zones. To understand that, you need to understand, well, how much water and weight percent is there in the downgoing oceanic crust. A lot of it is actually in the sediments and the pillow basalts. That's probably the first to go, and probably is the water that's feeding these forearc seafloor vents. Big uncertainty is what's happening down here in the mantle. So this is one calculation, one model based on an assumed 10% serpentinization of the upper mantle. But we don't have a good handle on how deep that goes. We don't have a good handle on how laterally variable that is in a global sense. So it's really hard to get a handle on it. If we could do much better models. Here's an attempt by Peter Van Kekken and others to try to look at the water flux coming out of the world's subduction zones. So I'm not going to go into this in detail, but the deeper colors here are more flux coming out. So most of the water, and then these stripes going back from each subduction zone, is at different depth ranges as the slab goes deeper and deeper. So most of the water probably coming out at shallow depths, feeding the forearc seafloor vents, and then a significant amount of water coming up to feed flux melting. But this is probably variable in ways, and so a lot of assumptions went into this numerical model to try to figure that out. But it's probably variable in ways that we have no handle on whatsoever, and it's really important from the point of view of fluid budgets. It's also really important if you want to understand the strength of the plate boundary. The world's most damaging earthquakes occur on this plate boundary in subduction zones. Right? That's the earthquake, the Tohoku earthquake last year that created all that damage in Japan. Was on a plate boundary up just like this, but up here. Whether you can get a strong earthquake depends a lot on the strength of the plate boundary itself, which in turn is going to depend a lot on, are there fluids there? Are those fluids overpressured? Are they creating serpentinite, which is kind of a slippery mineral compared to what would otherwise be there? This is from a paper by Akuko Wada, where she was looking at coupling of the plate. She's basically saying if you've got hydrous minerals and fluid pressures there, they're going to weaken the plate boundary. That's going to decouple it from the overlying mantle wedge, and the depth of that decoupling is going to have major impacts on temperature structure and petrological processes in the subduction zone. Intra-slab seismicity, really interesting fact about downgoing plates is there are earthquakes near the top of plate boundary, and there are also earthquakes inside the slab. These are called double seismic zones in downgoing plates. And it turns out that these faults may have everything to do with the depth of penetration of these faults, these plate bend faults, and then dehydration processes. So that water is now escaping. And as it goes out, you lose volume, and so you create little earthquakes. These are really spectacular double zones, double seismic zones. This is from a paper by Brad Hacker, where he basically says the lower seismic zone of double seismic zones is the result of serpentine or chlorite dehydration in the slab mantle. Another reason to care. We already talked about volcanochemistry. If we want to understand these volcano signals and where the slab component is to that, we need to understand how much water is going down in the downgoing plate and where it is released. And finally, the last thing I'll say is the thing I understand the least. This is from a paper that came out in Nature Geoscience just a couple of months ago in January. Life in the hydrated suboceanic mantle. And what they found was high concentrations of organic matter from fully serpentinized peridotite at the Mid-Atlantic Ridge. And they're saying that the life that this organic matter is the result of past microbial activity within the serpentinized oceanic crust, potentially supported by the byproducts of serpentinization. So this serpentinization, one of the reactions produces hydrogen. And this hydrogen that's produced as a byproduct of the serpentinization reaction could be used to support life. And frankly, I'm no longer surprised when I see a paper about a deep biosphere from someplace we never knew it existed before. I think if we could drill the core, we'd probably find microbes there. Wherever they can exist, they do. So if we're producing hydrogen here, and it's a place where microbes can get to, they're going to find it, they're going to use it. And so this serpentinization process might be hosting an entire deep biosphere that we know very little about. So I'll wrap it up with that then. So in conclusion, hopefully I've convinced you that reduced seismic velocities and other geophysical signatures like reflection signatures of faults and the low resistivity zones indicate that there's significant serpentinization going on in the oceanic crust and the upper mantle at subduction zones. That is the pathways of which are these plate bending faults. And serpentinization is often 10%, but can be 20 or maybe even 30% in places, and this has a wide array of consequences for a lot of really interesting earth and biological processes. So with that, I'll stop and thank you very much for coming. Do we?
Is there a relationship between the speed of subduction and serpentinization and faulting?
Yeah, that's a good question. So the plate velocities, how fast the plates are going into the subduction zone? Yes, but it's an indirect one in the sense that what's really controlling these dehydration reactions, and the hydration reactions for that matter, is the temperature pressure history of the rocks. So to the extent that the plate velocity has a big effect on the thermal evolution of the downgoing slab, that will have a control. So if you have, slabs are weird things. Is there chalk up here? Yes. Okay. So in general, when you go down, you go deeper in the earth, the temperature goes up, right? You're going closer to the core, temperature increases. That's not true in slabs. It's not true everywhere, right? Because you have a slab that is subducting down into the mantle. And out here in the oceanic lithosphere part, the temperature is increasing with depth. But over here, we're already, here's say a lithosphere asthenosphere boundary, we're already in upper mantle, hot upper mantle stuff. So the slabs are kind of strange because they get heated from above and from below. So you get these inverted geotherms where the coldest part of the slab is actually in the center, right? So this will be the last place to dehydrate any mineral bound water as it goes down. So the point of that is to get to your question. If you have a slab that's subducting faster plate velocity, there's not as much time for it to warm up. So you're probably going to be able to bypass these dehydration reactions and maybe send this water back down into the deep mantle. So that would be, I think, the main effect that the plate speed would have. It's on the thermal, because it's, these are slow. Plates move about as fast as your toenails grow or your fingernails for the fast plates. They're not moving very fast. So that's not going to have a dynamic effect on the faulting process or anything like that. But it does have a big effect on thermal evolution.
How big of a surprise was it to you and the other people who do this kind of work that these faults extended as far down as they do? Was that a big...
It was. I think it, it depends on the person. I think sometimes I'll admit it was a surprise to me. Sometimes you look back on discoveries and you say, oh yeah, of course, that makes total sense now. Now that we know that happens, it seems like it makes total sense. But I'll confess to having been surprised, and I even, I wasn't sure I believed this. I'm a seismologist. So I wasn't sure I believed the seismic images because I know how the sausage is made. Right? And so some of that in Renero's figure, some of that fabric of faults, it just looked kind of funny to me. That could have been artifacts if there was scattering or something in the processing. And and I asked Cesar about that, and he was really very convinced, which was good enough for me. Cesar's a good scientist, that those things are real. But I think, if you look at the amount of work that's happening in marine geophysics right now on this topic, it's really exploded in the last 10 years, and I think a lot of that is because of that image. It's a very visual image. It's the seafloor image that shows the faulting, and then combining that with the reflection image that shows how these things can go down very deep has really spurred a lot of interest. So I think that means it surprised a lot of people.
What do you hypothesize is the limiting factor as far as how far down this fault property?
Yeah, we could look at Facenda's model to get a handle on that, because that model, to the extent that the assumptions about rheology are good ones, is probably better than any intuition I could give you. But at the large scale, right? You're taking a plate and you're bending it. Well, if you bend, this is an engineering problem, right? You take a beam, you bend it. The top is an extension, but the bottom is in compression, right? So these extensional faults, you wouldn't expect to see them more than halfway down, at a fundamental intuitive level, halfway down the beam. That's basically what's happening. You're bending a beam, extension on the top, compression on the bottom. So it's cracking at the top.
You're saying it's a surface distribution and not the change in material properties.
Right. That's right.
I have a question on the equipment that you're using.
Mm-hmm.
Does it, when you get the information, does it go straight in the computer and already organizes the data for you, or do you have to do that by pulling it out and doing it yourself? So this is what graduate students are for. There's a lot of work. There's a lot of manual labor that goes. And so, the acquisition of the data is all highly computerized and automated. But you get basically files of seismic, seismograms, seismic amplitude versus time. And so organizing that information into something that looks like an image of the Earth, in the case of the reflection data, or something that looks like, that's a map of p-velocity, in the case of the wide-angle data, is a time-consuming process that is not easily automated. The reason why I'm asking is because I'm going to be I plan on wanting to build equipment and programming for the field. So it makes it easier, you can get your data faster and results quicker, so there's not so much hassle. And I wanted to know if there's any interest in that. I don't know if I should pursue it or...
Well, yes. I think these instruments. So it depends which instruments you're talking about. So the reflection stuff, like the hydrophone streamer, that's sending the data back in real time to a computer in the lab. There are big companies, oil service companies, geophysical service companies that design and develop that technology, and that technology is always improving. So
probably a tough place to just jump in and make an invention that's going to change the way that's done. With the ocean bottom seismometers, those ones that we deploy over the side and sink, those are all pretty much homemade at oceanographic institutions. The one that I showed you was one from Scripps Institution of Oceanography in San Diego. Woods Hole Oceanographic has some. Lamont Doherty has some. And those are all designed and built by small teams of engineers that are working in those labs to try to design something that's for very particular scientific use. Probably a lot more room for innovation in that field.
Yeah, because like I want to do underwater archaeology and get my master's in that. I think my bachelor's in geology, and I plan on building equipment. I'm going to get trade school with electronical wiring, gear programming, stick welding, so I can build stuff.
Yeah.
And I want to push the envelope. That's what I want to do.
Sounds great. Do it.
I'm glad you actually posted another volcanic chemistry, geochemistry one. Can you bring that up?
You want to see that figure again?
Yeah.
That one?
Yeah, when I saw that Nicaragua is actually in the center, has the most pressure and force on it, right? Well, it just looks like it's all your traits are peaking in the middle where everything has stronger velocity or.
You're talking about this peak here.
Yeah. And the other two are kind of like there.
Yeah. Yeah, I don't think that. So I guess I'm not sure what you're asking.
I forgot. It was that.
So I don't think there's any kind of pressure effect that would be along the trench.
The trait. The thing I'm trying to find is that reasonable trait for that. I don't even know what you're plotting on that anymore, but
Is this a reasonable?
like your high values
Yep.
are towards the middle of
Yep.
everything of your section.
Well, the section. I mean, you could take this farther up. It's just kind of a Central America. So the fact that this is in the middle, I don't think has any particular meaning. But I think so I didn't talk about this, but this is the dip angle of the slab, and that also this is how steeply is the slab dipping at depths of 100 to 200 kilometers, which is down where the volcanic source region is. And so there does seem to be a correlation there. So I don't think it's a pressure thing necessarily, but it's it's probably not as simple as I've been selling you that it's all got to do with the mantle serpentinization. These are complex systems.
That's not airline.
Yeah, well, right.
What's happening with the dipping water? It's like got some horizontal lines going on.
Yeah, this is a tear. So there's actually a tear in the slab. It's called the Quesada sharp contortion. And so it looks like the slab, rather than being, so you can imagine smooth changes in the dip angle would be just sort of undulations in the slab, but this is discontinuity. And so the idea is that there's a break in the slab there for reasons that I don't think anybody really understands. But there's actually a tear. So the slab dips much more steeply under Nicaragua than it does under Costa Rica, and that's the location of the tear.
Do you know if there's any kind of mineralogical differences between the area of the slab that's going under Costa Rica and the
Yes.
Would be accounting for that?
So you mean in terms of like the major element chemistry?
Yeah, so accounting in terms of like chemistry, like why? Well, for Nicaragua, I think there is a lot of that dip angle that's causing like. I figure like the deeper the dip angle, the more the fracturing you're going to get. So the more those weird trace elements you're going to get out of the serpentine. And then maybe that more shallow angle is why you're not getting as much in Costa Rica or Guatemala. But then if there's like some kind of, if it's not homogeneous across the entire plate for the trace elements, maybe that's also why we're getting that kind of non-consistency in Costa Rica, where it's also quite a bit steep. Right there.
So one of the nice things about this place is that most of these. So if you look at things like, and you can make a similar plot for beryllium-10, right, which is a cosmogenic isotope. So it's got to be something that it's got a half-life of 1 million years or so, 1.5 million, and means it was in contact with the atmosphere before subduction. Same kind of pattern. That pattern of sedimentation doesn't change much along the arc here. So I don't think so. The geochemists tell me this signal is not likely to be due to anything in the sediments and the downgoing plate. They're pretty uniform off of here. But there's definitely room for, and I think Mike Carr at Rutgers would disagree with the story about mantle serpentinization controlling this, but would say there's compartmentalization of the subduction zone, and you have different processes in these different zones that seem to be that's going to be having to do with the mantle wedge and flow patterns in the mantle wedge, the shape of the slab, the dip angle, all those kinds of things. It's a complicated system that could be driving a lot of these changes. It could also be have nothing to do with the upper mantle at all, and could just have to do with how much faulting there is trapping sediments at the top. You get faults, you get local accumulations of sediments, you can have more of these things. So it's a pretty complicated system. Yeah.
I was just going to be checking to see if we think there's a correlation between the amount of activity in the faults with the amount of degeneration.
The activity in the faults. Well, so I think you're asking about these figures here. Yeah. So if you map where earthquakes occur, just where are they? So I'm not talking about the level of activity in terms of the rates of seismicity, but just you get an earthquake map, where are they? And that's what this is a cartoon, but that's what these dots are meant to represent. And so this is actually data here from Japan. This is the island of Honshu. So these are hypocenters where earthquakes have occurred. And you see that they cluster in these two bands. And the upper band is easy to understand, right? That's the plate boundary. That's where the slipping is occurring between the downgoing plate and the mantle wedge. You'd expect there to be earthquakes on there. This lower seismic zone is a little bit harder to understand, and I think that there's an emerging consensus that what they represent is dehydration, the depth limit of these faults, and where dehydration reactions are occurring. I personally don't understand why you wouldn't have earthquakes in the zone in between, because presumably you'd be having dehydration reactions occurring all the way through there. So I would sort of expect a blur. And in some places you do see kind of a blur of hypocenters, but there's definitely a focusing at the base of these faults. It's got to be related to those faults. Does that answer your question?
Yeah.
Is there quite a bit of difference in the magnitude of the flakes?
Yes. So these are by far the strongest magnitudes are going to be in the upper zone, and these are much weaker. I don't want to put a number on that because I don't know off the top of my head. And since this is being videotaped, I don't want to go on record guessing. So I don't know, but certainly the strong earthquakes are the ones at the top. Yeah. Anybody else? All right. Thanks again for coming.